So, good afternoon, students. So, today we will discuss first the heating element material. What are the various properties that any of the heating material must require? First is high resistivity, high resistivity. So, first of all, you must clear that heating due to electrical current that will be generally given by I P is equal to I square R, right? So this is the major cause due to which heat will be produced. So here in this case, you may say that P is directly proportional to R. P means electrical power consumed, or due to this, heat will be just become element will be heated in any of the network, and we know that R is equal to rho L by A. Here rho is the resistivity, right? So that means if in this equation, if I need that heat of the element, heating of the element is more and more, then in that particular case, R must be high, right? R must be high, and from this it is directly shown that R is dependent upon resistivity of the material. Resistance is directly dependent upon the resistivity of the material. So if resistivity of the material is high, that means that particular element will produce high heat at the same current, right? If I will take the current of the same amount, and by considering the different element, then what we found that if the resistivity of the material will be high, then in that particular case, that material or that element will produce more heat as compared to the other. Now, second second property second property that is required, that is the high melting point. High melting point. So any of the material which will be used as a heating element, any of the material that will be used as a heating element, that must be having a high melting temperature. Why is it so? Because with the help of that heating element, I'm just going to heat maybe up to 1000 degrees C, or maybe up to 2000 degrees C, or maybe more than that. So if your material with the help of which your heating element is formulated, that is not that will be not suitable to withstand at that high temperature, then in that particular case, obviously your heating element will be melt, that will become in the molten state, and that would not be able to provide heat across the substance to which I want to be heat up, right? So the element which must be used as a heating element that must be used as a heating element that must have high melting point. Then after that, another property that I need is low temperature coefficient. Low temperature coefficient, right? So what does this mean? This means that here I am talking about alpha. Low temperature coefficient means alpha. So whenever alpha is value of the alpha is high, that means with the change in temperature, value of the resistance of that material that will vary sharply. Right? Value of the resistance of the material that will vary sharply. Fine. So if that any material which will be used as a heating element that is having a low temperature coefficient, then uh, it will respond very less with the change in temperature. That means its resistance will almost remain constant with the change in temperature. With the change in temperature, the resistance of the if the change in temperature, the resistance of the material will not vary or will vary very minute. Then in that particular case we are saying that that material is having low temperature coefficient. So this is another property which I need for the material to be used for the heating element, that is it must need low temperature coefficient. And other is that this the material which must be used for this heating element that must be free from oxidation, free from oxidation. So this is another property that the material for the heating element such that it may withstand the required temperature without getting oxidized. Otherwise, it would have to be replaced frequently. If that material be oxidized again and again, then we will have to change this. We will have to change this element again and again. So we must need some of that heating element which will obey these property or which may be capable to have these properties in that itself. So four different properties are there. One is high resistivity, second is high resistivity, second high melting point, third low temperature coefficient, and fourth is free from the oxidation. So the material commonly used for a heating element for low and medium temperature surfaces, that are the alloy of nickel and chromium, right? Nickel alloys of nickel and chromium, in which approximately 80% of the nickel and 20% of the chromium is there, right? That is commonly used for low and medium temperature services, right? And in addition to that, we may use alloys of nickel or chromium or iron, right? The addition of the iron of the alloy reduces the temperature at which oxidation takes place, but the cost of the product is also reduced. If generally we will prefer to use nickel or nickel chromium alloys, but on the other side we may add some iron in it also. If we are going to add iron in the alloy which is used as a heating element, then in that particular case what will happen, that oxidation takes place at lower temperature, but on the same side that element will become more economical, or you may say that the cost of the system will be reduced, right? So nickel chromium alloy is suitable for temperature up to 1150 degrees C. Nickel chromium alloy, that will be used up to temperature of 1150 degrees C, right? And on the other side, silicon carbide is the basic of the resistor material, which may be used up to temperature of 1500 degrees C. Silicon carbide is the material which may be utilized up to 1500 degrees C. Nickel chromium may be used up to 1150 degrees C, and this nickel, this silicon carbide is used at it up to the temperature of 1500 degrees C. If that alloy that will contain iron, chromium, cobalt, aluminium, that may be capable to withstand up to 1350 degrees C, right? So number of materials are there. If one more element, that is the tungsten. Tungsten is the material which may be used up to 2000, which may be used up to 2000 degrees C. If we need the temperature of up to 2000 degrees C, then up to 2000 degrees C, then we may use tungsten as the material, right? So graphite resistor are also suitable. Graphite resistor are also suitable for any temperature that can be used, and a resistor require protection against the oxidation above 600, about 600 degrees C, right? So here in this case, that three are the different types of the alloys. One is nickel chromium, another is silicon carbide, another is tungsten. This may be utilized for depending upon the temperature requirement. Depending upon the temperature requirement, we may use nickel chromium up to 1150 degrees C, silicon carbide up to temperature of 1500 degrees C, and tungsten up to the temperature of 2000 degrees C. Right. Now, after this, maximum operating voltage, maximum operating voltage. Now, in case of heating element, maximum operating voltage. Now, in case of the heating element, maximum operating limit is maximum operating voltage is limited. Maximum operating voltage is limited by electrical insulation at high temperature, and from the safety point of view, right? Depending upon the voltage, we must provide some insulation, and depending upon the voltage, we must acquire that high temperature, right? And we must maintain that level of the voltage up to 600 volt, level of the voltage up to 600 volt. This value may be exceed in special cases. This value may exceed, this value may exceed up to somewhat in some special cases, right? And resistor winding may be in one, two, or more circuit, and may be connected either to single or to the polyphase supply system. So generally, here we may say that maximum operating voltage is equal to 600 volt, but in special cases, this may exceed more than 600 volt, more than 600 volt. Why is it so? Because in this particular case, we also have to consider all important specification like insulation, temperature, right? Because depending upon the voltage, we must provide insulation across the network or across the element. Then after that, we must consider that temperature range, which will be also dependent upon the voltage applied across the circuit. So we, by considering all these factors, we must maintain that maximum operating voltage in general cases, that must be equal to 600 volt, and in special cases this may exceed more than 600 volt, right? Then yes, so next is this designing of the heating element. Now electrical input and its voltage, if we are aware with the electrical input and its voltage, size and length of the wire required as the heating element to produce the given temperature can be calculated, right? So if we are aware with the what is the voltage applied, then after that what is the electrical input, then we must be able to calculate what should be the length of the element that must required to attain the required temperature, right? The wire implied may be circular or may be rectangular like a ribbon. There are two options, that wire may be rectangular in shape like a ribbon, or this first may be circular in shape, right? If we are talking about that circular shape, then it permits the use of higher wattage per unit area, and this type of the wire will be used like in oven or toaster, etc. So heating element on reaching the steady state temperature will dissipate the heat from its surface equivalent to the electrical input, right? We are aware with the fact that energy can neither be created nor destroyed. It can be converted from one form to another form. So whatsoever input we will provide across the heating element in term of electrical energy, same will be available across the surface of that wire. Either it will be circular in shape, or that will be like a ribbon, that means like a that rectangular shape. So whatsoever input will be applied in term of electrical energy, same will be the output, if we are assuming that the system is an ideal system. If we are assuming that the system is ideal system, that means there will be no losses, input is equal to output. Then whatsoever electrical input is applied across the this circuit or this element, same will be available in term of heat energy across the surface, in of the heating element, right? So Generally the heat will be dissipated from the heating element at a high temperature. So it is reasonable to assume that the whole of the heating energy is dissipated solely by radiation, right? We are assuming that whole of the heat energy will be dissipated into the form of radiation, right? So heat dissipated according to Stephen's law, heat dissipated according to Stephen's law, that will be H is equal to 5.72. H is equal to 5.72 Ke into Ke into T1 upon 100, T1 upon 100 base to power 4 minus T2 upon 100 base to power 4 watt per meter square. So heat into the form of radiation, heat into the form of radiation, that will be given by this Stephen's relation or Stephen's law, that is equal to, as per that, H is equal to 5.72 Ke T1 upon 100 raised to power 4 minus T2 upon 100 raised to power 4 watt per meter square, right? So here these symbols are having its meaning, that is T1 is the temperature of the source, T2 is the temperature of the substance, T1 is the temperature of the source, T2 is the temperature of the substance, K, this is a constant, and it is known as radiant efficiency. K is a constant, and it is known as constant. It is known as radiant efficiency. K is unity for a single element, and this is between 0.5 and 0.8 for several elements placed side by side, right? And E is the emissivity, which is unity for black body and equal to 0.9 for resistance heating elements, right? So these different terms are having its own significance. T1, this is the temperature of the source, T2, this is the temperature of the substance, then K is the radiant efficiency, K is the radiant efficiency, and its value will be 1 if that material will be of single. K is a radiant efficiency, and it is equal to unity if that material is made of the single, if that element is made of the single material, and it will vary from 0.5 to 0.8. It will vary from 0.5 to 0.8 depending upon the combination of the material used. And E is the emissivity. For black body it is 1, and for heating element this will be between 0.8 to 0.9, right? So this is your Stephen's law output. Now we want to design this relation between that radius and length of the heating element. For that, we know that what is the electrical input. Electrical input, electrical input, that will be given by P is equal to V square upon R. Electrical input, that will be given by P is equal to V square upon R, where V is the supply voltage and where V is the supply voltage and R is the resistance of the heating element. Now we know that R is equal to rho L by A, right? R is equal to rho L over A, where L is the length of the heating element, A is the area of cross section, of the heating element, and rho is the resistivity of the material. Right? Rho is the resistivity of the material, L is the length of the area of cross section of the heating element, and A is the area of cross section of the material of the heating element. This will be different in case if it will be used as a rectangular strip or rectangular element, and it will be different if it will be used as a this circular shape wire, right? So here I am just substituting value of A is equal to pi d square upon 4 by assuming circular wire, by assuming circular wire your equation of the R will become R is equal to rho L upon pi d square upon 4, right? Here d is the diameter, pi d square upon 4. Here d is the diameter, L is the length, and rho is the resistivity of the material, right? Rho is the resistivity of the material, L is the length of the conductor, and D is the diameter of the material used, right? Now substitute this value. Let us say this is your equation number 1. This is this P. This is your equation number 2. This is your equation number 3. Now and this equation present equation number 4. Now substitute 4 in 2. Put equation 4 in equation 2. That means the value of R in equation of the electrical input. So that means it will become P is equal to V square upon rho L over pi d square over 4. So electrical power input across the heating element, that will be given by V square upon 4 rho L over this 4 will be on this side, so this will become V square upon 4 rho L over pi d square, right? So this is your electrical power input. This is the electrical power input across the heating element. Now from this equation you may calculate the value of L over D square. From this last equation, let us say this is your equation number 5. This is your equation number 5. From this equation 5, calculate the value of L over D square. So from this denominator, you will get P into this complete term. This will be moved on the other side. So this will become 4 rho L over pi d square. This is equal to V square or V square upon P is equal to 4 rho L over pi d square. So from this, L over d square is equal to 4 rho V square upon pi into P. L over d square is equal to pi V square just see this. From this equation itself, P is equal to V square pi d square over 4 rho L, right? So from this, L over d square, this term, this will be move on the other side. So this will be V square pi over 4 rho P. So L over d square, that will be given by V square pi over 4 rho into P. So surface area, we know that surface area S is equal to pi dl. Surface area is equal to pi dl, right? So if this H surface area is equal to pi dl, this is the surface area, right? So if this equation pi dl, this is the surface area, and at the start, when we write that Stephen's law, we write that that will be watt per meter square. H is equal to 5.72 ke into T1 upon 100 base to power 4 minus T2 upon 100 base to power 4 watt per meter square. That means that is the heat dissipated by the element, per unit area, and this is the total area, right? Total surface area, that will be pi dl, right? So here from this, what will be the total heat dissipated? Total heat dissipated, that will be given by H into pi dl. H is what? That will be the Stephen's heat or Stephen's formula, right? H into pi dl. H is the Stephen. H may be calculated from the Stephen's formula, right? Since at study temperature, we know that power input is equal to heat dissipated. If we are assuming, if system is assumed to be lossless, that means ideal condition, then what we are saying, that P is equal to electrical power input, that will be equal to pi dl into H. P is equal to pi dl into H, right? So we had calculated that value of this P, from the previous equation. This is your value of P, right? So here substitute, let us say this is your next equation. Substitute the value of P from this upper equation in this equation, right? So what you will calculate that I'm just substituting the value of P here, V square pi d square upon 4 rho L, right? This is equal to pi d L into H. I substitute this value of P in this equation. From this, calculate the value of d upon L square. From this, you may see this d will be cancelled out. L will be multiplied on this side. You will get V square pi d upon 4 rho L square is equal to pi into H, right? I had d, 1d will be cancelled out, 1d that will be cancelled out. That's why d square will remain as d. Then after that L will be multiplied in the denominator. So from this d over L square is equal to pi H 4 pi H rho over pi again gets cancelled out. So 4 rho H over V square 4 rho H over D square over V square. This is the value of D over L square, and in the previous equation, we just calculate that value of L over D square. One equation that we had calculated, that will be L over D square is equal to pi V square. L over D square is equal to pi V square over this L over D square is equal to pi V square over 4 rho P. 4 rho P, right? So here one equation is D over L square, another is L over D square. So by solving these two equations, length and diameter of the wire can be calculated. If in one equation, let us say this is your two equations, right? So by solving these two equations, one is the equation of L over D square, another is the equation of D over L square. You will be able to calculate two equation, two variable, as all that parameter are known to us. So by calculating, by just solving these two equations, you will be you will be able to calculate the value of L and D for the heating element, right? Now one thing, this is the case if we are assuming that, the wire is circular in shape. If the wire is assumed to be rectangular, that is ribbon like conductor is utilized as a heating element, then we are assuming that let W is equal to then in that particular case, if we are assuming that this conductor is rectangular in shape, then we are just assuming that let W and T, W is the width of the conductor and T, W is the width of the conductor and T is the W is the width of the conductor and T is the thickness of the conductor, then your relation will be like P is equal to V square upon R, right? P is equal to electrical input, P is equal to V square upon R. Now this will be V square upon rho L over A, and here this area will be equal to V square upon rho L over W into T, width into thickness. That will be area of cross section of the conductor, area of cross section of the conductor if the material will be like rectangular shape, right? So in this case, you may calculate that value of L upon WT from this equation. Here this is the equation of P. So L upon WT, that will be equal to, you may calculate this equation, L upon WT is equal to V square upon rho P, V square upon rho into P, right? So from this, at steady state, again we are assuming that under the ideal condition, power input is equal to heat. Power input is equal to heat. So P is equal to 2W, P is equal to 2WL, actually W into L. This is the area of cross section of one side, and rectangular is having two different sides, right? So that's why I am multiplying it with 2. This is the area of cross section. Then H, again, this is the H is the area, H is the heat per unit area of cross section as per the Stephen law. So P is equal to 2WL into H. H will be same as that of the previous case. So here we substitute the value of P. P is equal to V square WT upon rho V square into WT upon rho L is equal to 2WL into H, right? 2WL into H. So from this, you may calculate that T upon L square, as L will be multiplied, T upon L square, this will be equal to 2WH over rho V square into W again gets cancelled out. So T upon L square is equal to 2H rho over V square. 2H rho over V square. So by solving two equation, one is having the value of L upon WT, one is having the value of L upon WT, and second is having the value of this T upon L square. By solving these two equations, you may calculate that value of the length and thickness. Length and thickness of the ribbon type conductor may be calculated by using these two relations. By solving these two relations, you will be able to calculate the value of length and value of area of cross section, value of the thickness of the ribbon type conductor. So there will be two cases in designing of the conductor. In one case, there will be, we are assuming that the conductor is circular in shape, and in that case, we will have to calculate L and D, length of the conductor and diameter of the conductor. In second case, we are assuming that the conductor is rectangular in shape. That means conductor is like a ribbon. So in that case, by solving these two equations, you will be able to calculate length of the conductor as well as thickness of the conductor. So by using these two different conditions, you must be able to calculate, depending upon the temperature and depending upon the voltage applied, what should be the length of the conductor and what should be the diameter or length and thickness of the conductor as per the material use. This is the end of the lecture, right? So we will meet in next lecture again. Thank you.